This is lecture 22 of CS147 Computer Architecture Study. In this lecture, we'll be talking about the cache performance computations, related problems, and how to improve the cache performance. So, to start with, let's review our performance numbers with respect to these cache penalties and memory stall, etc. The concept we just learned about in previous lectures. So, our CPU time is basically now, with respect to this whole concept of memory stalling and stuff like that, it is basically number of cycle that CPU execute plus number of cycles that there is a stall for the memory because of the cache miss and copying back the memories from the lower block to the higher block or lower memory to the higher memory, copy those blocks. You need some times to do that, and they are included in the memory stall cycle. So we need to add now these two different type of cycles to compute the total number of cycle for the execution, and then multiply with the time period of per clock, time period of the clock, and that gives you total amount of time done needed to be for the program. Now, how to calculate the memory stall cycle? Right. So, memory stall is categorized as two different operations. For read operations, how many stalls, and write operations are how many stalls. Read stall cycles, we can imagine that this is the percentage or ratio of your read, number of read done compared to, let's say, total number of instructions. Okay, number of instruction of read compared to total number of instruction in the program that is being executed. So you take the ratio, multiply with the I total, that will give you number of instruction for the read operation has been done in that program. So you can say that why is this thing, this is why don't we just say in terms of read, because usually you will be given, or you'll be knowing that the number of total instruction has been executed on the processor, and how much percentage of that instruction, total number of instruction, is a read instruction. So that's why it is basically we are taking the ratio of read and write. That is one parameter, and other parameter is your total number of instruction. Then with that we compute the number of read involved in a miss. So this is a miss rate, MR, miss rate for the read, and then we multiply that with the penalty for the read miss. So penalty in terms of number of cycle, how many cycle you need for that, for cache miss, one cache miss. So essentially we are talking about total number of read instruction multiplied with the miss rate. So that will give you number of instruction that involved penalty for copying the blocks from the lower memory to higher memory. Multiply that with the penalty, number of cycles as a penalty. The write cycle stall is the similar, but for the write through strategy with a buffer inside the memory module that we discussed in the earlier lectures, we need to add those number of cycle for the buffer stall. Either it will be given directly or will be given in terms of the percentage of the read stall and so on and so forth. Just watch out for the statement and what information you have given. But at the end of the day, you need to compute this number of cycles spent as a buffer stall. And rest of them is basically your percentage of write instruction multiplied by total number of instruction multiplied by miss rate of the write multiplied by the penalty involved in the miss rate, write miss, and that gives you number of cycle for the write stall. So usually a write buffer of depth 4 or more, write buffer stall come to a very small number. So we can actually ignore from our equation in most of the cases unless it is specified to you. If the stall is still high in a practical situation, what we need to do is either increase the depth of the buffer or depth of the queue in the memory model, or move to the write back strategy, implement write back strategy for the system. Now in this case, if we assume that your buffer is efficient and there is very like buffers stall due to due to the buffer overflow, it's very small, then we can eliminate that and your C write stall becomes your the same expression, except we don't add the cycles for the buffer stall here. Now usually read and write penalties are the same, because for both of the cases what we need to do, we basically need to copy the memory from the what to higher memories for write through strategy. For the write back strategy, you need to first make the dirty block, copy it back to the lower memory, and then pick up the new block and copy it to the higher memory. So for write back cache, both read and write miss will need to write back dirty cache. Okay, yeah. So this is the 2 points I was mentioning. So usually we can say that the memory stall is basically number of memory access with miss rate on the memory access and penalty of that penalty per miss. So unless otherwise specified, specifically you have a different read stall, different write stall, it's basically all accounted for the memory access stall, read or write independent. Let's take one problem example. Okay, so this problem says assumes the instruction cache miss rate is 2% and data cache miss rate is 4%. Okay, so remember we have two type of caches in the system. Now if a processor has a CPA of 2 without any memory stall and the miss penalty is 100 cycle for all the misses, means here is not all the misses means accounting all the miss, but all types of miss, determine how much faster a processor would run with a perfect cache that never missed, assuming there are 36% instruction is a memory instruction. Okay, so what we are trying to do here, we are given with the 36% of the total instruction as a memory instruction. We have given with the miss rate for the data cache and instruction cache, and said that a processor takes 2 CPI if without any memory stall, and if there is a miss, then it incur 100 cycle extra. Okay, so we need to determine how much faster this processor would run with a perfect cache, which means your miss rate is 0% for both instruction and data cache. To solve this problem, we start with the assumption our total number of instruction is I. Okay, so then cycle for the instruction miss. Okay, it's basically I into 0.02, that is 2%, and to multiplied by 100, which is basically 2 into I. And the data miss is basically your 36% of the instruction is a data access. So first one, C instruction miss, is when we are accessing the memory instruction cache for your instruction fetch, that time how much miss happens. Okay, so that's what the 0.2% directly multiplied by I multiplied by 100 cycles, so your number of cycle is 2I. Now data miss is out of this I, total number of I, 0.36 of them is your data access instruction, like load word or store word, which incurs a 4% miss rate, 0.04 multiplied by 100, which gives you 1.44 I as a number of cycle for the data miss. That means your memory, total memory stall you are incurring here is add up of these two, C instruction miss and C data miss. That comes to 3.44 I. That means the cycle with the average stall per instruction is 3.44. So hence the average CPI would be your 2 plus 3.44 is 5.44. That is the CPI. So your base CPI is 2 here, and you are incurring 3.44 I of that many cycles for your memory stall. That means per instruction, that cycle per instruction for this stall in average is 3.44. So we add them up to make an average CPI of this whole system as 5.44. That means if we want to compare the performance, which comes down to ultimately total number of time or execution time for the CPU with the stall by CPU with the perfect cache. So CPU with the stall is basically they're running with the same clock, same number of instructions. Those will be cancelled out from numerator and denominator, and it becomes a ratio of the CPI for the stall, a machine with a stall, by CPI of the machine with a perfect cache. So it becomes a perfect cache, no miss. That means CPI is still 2. Your machine with the stall CPI is 5.44. You ratio them, it's 2.72. So perfect cache would be running 2.72x faster than the one given in this example. Now this introduction of this memory stall actually gives us very unique perspective of how we are going to make a system faster. Here is what I mean by that. Now, if a computing system is made faster without improving the memory system speed, the slowdown become more. Means with respect to a system with a perfect cache, like with system with a no slowdown. Okay, so of course there would be slowdown and stuff like that in a normal sense, but we are kind of comparing with an ideal computing environment with this target computing environment, right? So in previous problem, that's what we did. This is what we had for the machine with a stall, and then a perfect machine, right? Now, if a computing system, let's say your total execution time has two parts, one is the CPU time and another is the memory access time, and you improve on the CPU time without improving the memory access time, taking care of the stall and etc. Maybe you need to speed up the memory with the new technology and so forth. But let's say you didn't do that, then your slowdown with respect to the ideal system would be more. That comparison would be more. Like, for example, in this previous example, if the CPI is improved to be 1, like we are making the CPU faster, what would be the performance difference of the cache with the stall and without stall? So in this problem, your CPI perfect is 1. The new CPI with the stall, because you're improving on the CPI of the machine of the CPU, but you're not taking care of anything with the stall. Your stall CPI would still remain 3.44, whereas you improve the CPI. Remember that in the previous problem we added 2 plus 3.54 and that becomes 5.44. Now it is 1.1 plus 3.44, which is 4.44, and now you see performance comparison become actually 4.4x. That means we improve the CPU, but with compared to the perfect machine, and we didn't do anything about the stall, we have more performance difference with the perfect machine. So before, previous difference was about 2.72x, now it becomes 4.4x. Now take another problem. It's the previous example, if the clock frequency of the CPU is is double, then what would be performance comparison between the system, the cache miss and perfect cache? Now, this problem assumes this your memory speed remains same. Your in the previous example, same clock was driving your CPU and memory. Now you improved on the CPU clock frequency. That means you can take the faster clock now, but without improving the memory clock. Okay. So since the memory speed remain the same, the miss penalty will be doubled. That means 200, right? So we are computing the miss penalty with respect to the clock of the CPU. Okay, so since your memory is now 2x lower, right, it's running on the 2x lower clock compared to the CPU, your penalty will become double in that case. So it is 200 now miss penalty. And we recompute the miss penalty, which comes to be 6.88. So faster computer with the cache miss will have effective CPI as 2 plus 6.8, which is 8.88. Now we compare them, okay, execution time with the slow clock and the fast clock, then CPI slow clock, fast clock, etc. We need to take care of that clock cycle by 2, that is your faster clock's time period, and which becomes 1.23x. So previously it was 2.72x. So if we, so this is what we are trying to show here. If we actually go and improve the CPU frequency, CPU clock frequency, then we actually improve better. I'd say your performance difference with an ideal system versus a system with a stall, the difference would be less. Now in this case it's 1.23x, but compared to the previous one, the previous one, that problem, it was 2.72. That means kind of relative performance improvement should be targeted on the frequency side first of all. And if we want to also tune up our CPI on the CPU, we also take care of the memory performance by reducing the stall in the for the miss, like we reduce the miss penalty. We need to work on that as well.